Hello PLP Geometry and welcome to the second lesson of Unit 4. So again, let's remind ourselves that Unit 4 is titled Similarity. Similarity and right triangles. And this is video 2. And we are going to cover what are called similarity transformations. Similarity transformations. Transformations. So we are going to kind of tie this into Unit 2. Where we did transformations of rigid motions, reflections, translations, rotations, but now we're going to throw in what we learned last lesson, dilations, into this section. Now, before we begin, let's talk about this word similarity or similar, right? So we did congruence back in topic 2 when we did those triangle congruent proofs. Well, now we're going to talk about similar figures. So similar figures. And I mean, more importantly, it's going to be similar triangles is what we're going to end with, right? That's going to be, I think, the next lesson. So if your two triangles or two figures are similar, then the corresponding angles, I can't ever close my A's, I'm sorry. The corresponding angles are, just close that one, are congruent, but, and this is a big but corresponding sides are, and it's a algebra word, proportional. And it's a big deal. Corresponding sides are proportional. This is the big difference between congruent figures and similar figures, is that in congruent figures, the corresponding sides are also congruent, but in similar figures, the corresponding sides are proportional. And again, if you remember from last lesson on dilations, the figures are not the same size. One is bigger than the other, so that's why this idea of proportionality works. So let's draw two triangles. We're going to make them two obtuse triangles. So here's triangle LKM. So LKM. And let's do triangle SRT, and it's going to be smaller, but again, looking the same shape as best you can. S, R, and T. So LKM, SRT. So if I tell you that these two triangles are similar, I would write a triangle similarity statement. So it's a triangle, and we'll go alphabetical order. KLM is similar. So notice the similar symbol. It does not have the equal to like the congruent symbol. It's just the top part, right? So keep that in mind. So triangle KLM is similar to triangle RST. So what this means is your corresponding angles are congruent. So angle K is congruent to angle R. So angle K is congruent to angle R. Angle L is congruent to angle S. And then angle M is congruent to angle T. So there's your corresponding angles being congruent. But I'm going to change colors to blue because it's a big deal. But now, your corresponding sides are proportional. What this means is that the ratio between the image and the pre-image are the same. So for instance, RS, the length of RS, compared to the length of KL, so those are corresponding sides, RS and KL, will be the same as the length of ST compared to LM, will be the same as the length of RT compared to km. This is what I mean by corresponding sides are proportional. If you put them in a fraction, you get the same simplified fraction or decimal. Remember, this has to do with scale factor. So I'm going to put this in parentheses. Scale factor. Keep that in mind as you think about how these similar triangles work. Okay, so let's talk about what it means to be a similarity transformation. All right. So to be a similarity transformation, similarity transformation. So that's dark, so I'm going to make it a little lighter purple. There we go. Sorry about that. To be a similarity transformation, this means you are going to map. So a similarity transformation maps one figure onto another using one rigid motion. So, and again, let's remind ourselves that our rigid motions are reflections. That's a reflection, a translation, or rotation, and a dilation. And that's the most important part, right? So again, it's going to take a reflection, translation, and a rotation, and then a dilation to map the one figure onto the other. Okay? So I'm going to walk you through an example of a delta math question you might see. Okay, so I'm going to walk you through this problem. So it's to determine a series of transformations that would map polygon ABCD onto polygon A prime, B prime, C prime, D prime. So sorry, it's not a triangle, so you might get more than just triangles. So I need to line up, right, A, B, C, D, and A prime, B prime, C prime. So first of all, I would like these two figures to be in the same quadrant. Right now, the pre-image A, B, C, D is on the left in quadrant 3, and A prime, B prime, C prime, D prime is in the quadrant on the right. So the first thing I want to do is I want to bring the pink triangle into quadrant 4. To do that, I think I have to reflect. Right? Again, if you look at A and D in the pink, it's on the right, but A prime, D prime is on the left, so I think I got to kind of flip this thing around. And I'm going to reflect it across this axis, which is the y-axis. And I'm going to click try. It's going to actually do the movement for me. Okay. So now if you look there, and let's see, hopefully I can write on this. I can. So if you look there, so this point A, give me 1 second. This point A went right here. Okay? So the new coordinates of A, so the original coordinates of A. So A was at -6, -3. Now, when I reflected A, now A is at 6, -3. Now, I want to compare that to A prime. A prime's coordinates are at 2, -1. So, can you think, right? Think about what number would I have to multiply these two coordinates by? What would I have to multiply 6 by? I'm going to put an n. So 6n and -3n. What would I have to multiply 6 by to get 2? What would I have to multiply -3 by to get -1? Well, obviously we're getting smaller, right? This is a reduction. So therefore your n must be less than 1. So to solve for n, what I would simply do is for this top equation, so 6n equals 2, I divide by 6. and I would get n equals 0.3 repeated, which is 1/3. And that is the factor, the scale factor, that I must dilate by. So if you take a look here, I next need to do a dilation. Center to the origin by a scale factor of, and again, I'm going to type in 1/3. And I'm going to click try. Okay, so there we go. And then when I dilate by a scale factor of 1/3, boom, I'm right on top of it. And there it is. Green check mark. All right, let me do one more for you. Okay, so again, describe a series of transformations that would map a polygon. So again, sorry, five vertices, A, B, C, D, E, onto A prime, B prime, C prime, D prime, E prime. So pink triangles where we're starting. This is the pre-image. Blue is the image. We are in quadrant 4 with the pink. We need to get to quadrant 3 with the blue. So right now, if you look at this figure, A is at the top left in the pink, but then A prime's on the top right in the blue. So I think I need to take this pink figure and turn it. And I only have to turn it like 90 degrees clockwise. Or if I go counterclockwise, I have to go 1, 2, 3 quadrants, or 270 counterclockwise. So let's take a look at what they tell me. Rotation. So notice it says counterclockwise. So I could go 90 clockwise or 270 counterclockwise. So I got to go 270. Again, 3 quadrants. And let me try that. Okay, so you see right now, and we'll use point A again. Okay, so point A originally was at 1, 1. Now point A is at negative 1, 1. Okay, now let's compare that to A prime's coordinates. A prime's coordinates are at negative 3, negative 3. So again, I think you can see that the pink figure is smaller than the blue, so this is an enlargement. Enlargement. Your scale factor is going to be bigger than 1. So the question is, I apologize, 1 second. Let's go back to here. So A moved to negative 1, negative 1. So I apologize. So this should be negative 1, negative 1. I apologize. So now the question is, what must I do with these coordinates? What number must I multiply them by to get from negative 1 to negative 3? From negative 1 to negative 3. What scale factor must I multiply by? So to do this, I can just do negative 1 times n equals negative 3. I can divide by negative 1 to get n equals 3. And there's my scale factor of 3. If I make these coordinates become 3 times larger, I will get the new figure. So I'm going to dilate, and my scale factor will be 3. And if I click try again, there's my 270 rotation, there's my enlargement by 3, and boom, they line up, and we're good to go. Okay? So we're going to stick to those 2 types of problems. Reflection and a dilation, and a rotation and a dilation. All right, last thing I have to show you, back on the notes. So the state test wants me to tell you one more thing about similarity. Okay, this is a question that's always on the state test. I'll do it in green. So last thing. And we haven't really talked about these yet, but this is where I'm going to fit it in. All circles are similar. And again, I'm doing this because of the geometry OST. So, for instance, all right, say I have a circle with a center of A and a radius of R. I want to map it onto a circle with center of B, radius of S. So somehow, some way, I need to move this circle so that A and B line up. So step 1, you need A to correspond or go to B. And typically we do this with a translation. So I would just simply slide this circle so that A and B line up. So I'd slide the circle this way. So A and B would be the same point, but now circle A is smaller than circle B. So it'd look like this. And this would be your radius of r. We call these circles concentric because they have the same center. Okay. Then, step 2, we would dilate the new circle A by a scale factor of n equal to the new radius in this problem, which would be S, divided by the old radius in this problem, which would be R, or the original. And when I do that, it would make circle A become big, and it would go on top. It would go on top of circle B, and that would be the similarity transformation to move circle A onto circle B. And again, all circles are the same shape. They're all circles. They're just different sizes. So that's why we have to dilate with the radii. All right, thanks for watching here. Good luck on your practice.